Hey everybody, I hope that you guys are having a good start to your day. I hope that you've enjoyed your week so far, and I hope that tonight, on the 12th of September, you go to the Bobcats football game if you have the opportunity to. Um, One of my other classes, one of my students called for Cats by 90, so let's go ahead and aim for that. I think that showing up, you can do your part by yelling and everything like that. Okay, cool. Well, we have a meeting and a discussion tomorrow on Zoom. I will be posting and recording that, where I'll be working through a little bit of the study guide that I put together, answering questions. By then, I should have the exam written, so I'll be able to answer questions and kind of give you some more details about the exam. Now, with that said, this is our last bit of new material for this exam. We had a total of 6 PowerPoints for that exam, so a good bit of material, but I would say not too much, not unbearable. Um, and so this is going to be our last day of new content. And for this, we're doing more functional groups. Now, to break this down, this group was what we did. I guess that would have been on the 9/5. We talked about alcohols last time. We talked about a couple of different functional groups and really kind of narrowed those down. We're going to go after some more functional groups. Now, as I said last time, the comprehensive list of functional groups that was provided for y'all, you do not have to have those memorized or anything like that. What I want you to know about are the functional groups that really were the meat of each of our lectures. So with that said, our first is going to be the phenols. Phenols are organic compounds with hydroxyl groups attached to an aromatic compound. So we talked about aromatic compounds last time, where we used as an example benzene as an aromatic compound. And if you remember, we looked at benzene and we said, oh, well, this is one structure of benzene. And then this right here is another structure of benzene, where the difference between them is the placement of those double bonds. And one of the things that we talked about was, well, structure A versus structure B. Well, A isn't more right than B. More accurately, the structure of benzene is kind of a combination of those two. So now this is this is an example of an aromatic compound. Now, phenols are stronger acids than alcohols, and they're known to be very toxic. Phenols can also hydrogen bond because they have a hydroxyl functional group. So a little bit more accurate. Let me go ahead and I'm going to scribble this out, block this out. So just imagine, oh wait, I've got a better idea than that. Now let's go to ink color white. It's like it does not exist at all. And then let's see if I can trace it. I can trace it not particularly well. And I'm not going to waste a lot of time on that, but instead, a hydroxyl group, what that looks like is this is an oxygen with electrons and another pair of electrons. That means that this phenol right here with lone pairs of electrons can act as a hydrogen bond acceptor. Now, this hydroxyl group also has a hydrogen, so it can act as a hydrogen bond donor. Now, the depiction that we get right here, let me erase all my writing there, shows this dashed line. That indicates a hydrogen bond. Now, that dashed line is not a covalent bond, but instead it's a hydrogen bond. Be able to distinguish between those. That's a great exam question. Now, what that means is that this phenol that I'm highlighting really acts well as a hydrogen bond donor. So I'm going to say H bond donor. Now, it's that hydroxyl group that allows that, but alternatively, they can act as what's known as a phenoxide ion. Now, that's an ion, so it has an overall charge. This charge is -1. How does a phenoxide ion come to exist? Well, this hydrogen right here gets released. So phenol releases that hydrogen, and we arrive back at a phenoxide ion. So whenever it's acting as when phenol acts as an acid and gives up a proton, well, then we form a phenoxide ion. And this is a very toxic substance. Alternatively, what phenol is very capable and kind of likes to do is it likes to form hydrogen bonds. So you can have phenol-phenol bonding or phenol-phenol hydrogen bonding that takes place, which is what we depict here. So these are all things that happen with phenol, and these are the important details of phenol. One, it's an organic compound with a hydroxyl group, but more important than that, it's an aromatic organic compound with a hydroxide group or a hydroxyl group. Now, our next functional group is going to be our ethers and our epoxides. Let's tackle our ethers first. An ether, which you've probably heard that term before, usually when people describe something that they describe something and, well, I just put it out into the universe. Sometimes people will say something like, and into the ether it goes. Well, more specifically, more concretely for a chemistry class, an ether is a molecule with two organic compounds attached to the same oxygen atom. So a hallmark of an ether looks a little bit like this, where we have an oxygen atom, and then this R right here and this R right here are your examples for your organic compounds. So this organic compound could be, well, it could be H3C. It could be CH2CH3. Okay, so that would be an example of an ether. Now, here's another example of what's known as diethyl ether. This is ethane. This is also ethane. These two ethanes are both bound to a central oxygen. Oh, no, I didn't mean to scribble that out. A central oxygen right here, which is why we refer to this as diethyl. So two ethyls, diethyl ether. Now, ethers can be an open chain or a ring. Now, ethers that are 3-atom rings are called epoxides. Okay, so an epoxide, is that any ring? No, it's not. Epoxides are 3-atom rings. So this right here is an epoxide. This is also known as ethylene oxide. Now, diethyl ether right here can cause you to become unconscious, depending on if it's inhaled or not. So the last of our 4 molecules that's shown below, this guy right over here on the far right, tetrahydrofuran. Okay, so let's dissect this and let's use the terms that we're talking about. Okay, an ether is a molecule with 2 organic compounds attached to the same oxygen. Okay, so oxygen atom. Boom, right there. Okay, ethers can be an open chain, which is what we've got here with diethyl ether or dimethyl ether. Ethers that are 3-atom rings are called epoxides. Okay, and can an ether be a ringed molecule? Yeah, and we see that right down here with our ethylene oxide. This is our epoxide. This is a 3-membered ring. 1, 2, 3 atoms. So this is an epoxide. We're sharing an oxygen. Done. Okay, now let's go over to tetrahydrofuran. First question, is that an epoxide? Well, our definition for an epoxide is that it has 3 atoms. Let's go ahead and do some counting here. 1, 2, 3, 4, 5. So 5 atoms. Is this an epoxide? Nope, it's not. Is it tempting to want to call it an epoxide? I think so, because I think, well, it's an ether and it's a ring. I should probably call it an epoxide. No, epoxide is reserved for 3-atom rings. Now, does that mean that this is the only epoxide? No, not at all. That's a 3-atom ring, and then that's a modification to that 3-atom ring. Is this a 3-atom ring? It is. It's an epoxide with modifications to it. So is this molecule right here that I drew, is that an epoxide? Yes, it is, because it has that 3-atom ring structure. So now when we go down to tetrahydrofuran, well, that is an extremely explosive substance, and that is an ether. Okay, so ethers and epoxides. In epoxide, I always think of like ethers as like a big umbrella, and underneath that are epoxides. Epoxides are an example of an ether. All right, now next up are aldehydes and ketones. Aldehydes and ketones are two families of organic compounds that contain a carbonyl functional group. C double bonded to an oxygen. So carbon double bonded to an oxygen. So this right here, keep that in mind. And, I like to ask questions where I'll say something like this right here, H3C, C. I could ask you the question, does this molecule have a carbonyl functional group? The answer is yes. I could throw the same molecule at you and ask you, is this an aldehyde or is this a ketone? Now, whenever I ask that question, the presumption is that it has a carbonyl. Yeah, so we've established that. But then what we're asked to do is look at this molecule, compare it to this, or compare it to this. Aldehydes and ketones are both molecules that have carbonyl carbons. So here's our carbon. Boom. Here's our carbon. Boom. There's our carbonyl carbon for both of them. What makes aldehydes and ketones different from one another then? Well, the important thing to distinguish an aldehyde from a ketone is what is attached to that carbonyl carbon. This R group right here, it could be any number of things. R group is kind of it's an organic chemist or a chemist way of saying, oh yeah, there's something else there. There's also a hydrogen. Okay, so when you see aldehyde, what I want you to think is organic molecule plus carbonyl plus hydrogen. So organic plus carbonyl plus hydrogen. Okay, so that's an aldehyde. Now, the difference between an aldehyde and a ketone is, well, what comes after that carbonyl? Well, in the case of a ketone, you have organic carbonyl plus organic. So this would be something like CH3. Okay, so that's our structure for a ketone versus an aldehyde. So anytime, like if I were to draw a molecule like this, and I were to say, okay, well, based on this molecule, is this based on what I've drawn there, and I'm going to leave this as a blank. I'm not telling you what's there. Is this an aldehyde or a ketone? Well, I've drawn a blank there. So you really cannot answer that question. You can't say if it's an aldehyde or a ketone, because if this is a single hydrogen, then it's an aldehyde. If this, by comparison, is a CH3, then that's a ketone. So that's how we distinguish aldehydes from ketones and vice versa. So just as a review, what we talked about so far are phenols. That is an aromatic molecule with a hydroxyl group. We've talked about esters and epoxides. We've got an oxygen there. So if you're thinking about a theme, well, we're talking about compounds that have oxygen. So a phenol has a hydroxyl group. An ester or an epoxide also has an oxygen, but that oxygen is only bound to organic molecules. Then we've got our aldehydes, where we have a carbonyl. So that sometimes this whole group right here is called a carbonyl group. Sometimes I will say a carbonyl carbon or a carbonyl oxygen. but we have a carbon double bonded to an oxygen for an aldehyde or a ketone. Now, next up is kind of bringing a couple more things together. Organic compounds contain a carboxyl functional group. A carboxyl functional group takes a carbonyl and then it adds to that a hydroxyl group. And it looks like this. So here is our kind of classical carbonyl. So if let's just go, I'm going to put an R right here. And then I'm going to scribble this out. So far, what we've looked at is if you see this, you might think, oh, it's an aldehyde or a ketone. And then you'd say, all right, well, if I have a hydrogen there, then it's an aldehyde. If I have a organic molecule there, then it's ketone. But then a carboxylic acid throws at you a curveball where rather than an organic or a hydrogen, you have a hydroxide group, which is the same thing that we threw on to make a phenol. Okay, so we have a hydroxyl group there. This is our this is a carboxyl functional group. Carboxyl functional groups are, and this is one word that I always like to say synonymous with. And they're always seen in molecules known as carboxylic acids. So let me just go ahead and make a minor modification. This right here is your carboxyl. As soon as you add an organic group here, then it's a carboxylic acid. And that's important to recognize because what that means is that this molecule right here, this carboxylic acid, what it likes to do is it likes to take this hydrogen and release it and give it away, act as an acid, donate that proton to something else. Now, these are great examples of organic acids. Now, if you think back to whenever you talked about acids and bases in your previous chemistry class, you talked about things like HCl. That's a strong acid. Now, I want to ask you this question. HCl consists of hydrogen and chlorine, and that's it. Is HCl an organic acid? Now, before you answer that question, think about what constitutes an organic molecule. What's the important part about the study of organic chemistry? With organic chemistry, you're studying molecules that are carbon-based. So they have carbons, hydrogens, oxygens, they have some other things, but mostly they've got carbon. Does HCl have any carbons hidden anywhere? No, it doesn't. So by virtue of not having any carbons, this is not an organic acid. Now, I bring this up because there are some organic acids that you're familiar with. One that you're familiar with from the beginning of this lecture was phenol. Phenol is a carbon-based acid. It's an example of an organic acid. Carboxylic acids are organic acids that contain carboxyl functional groups. Now, in terms of things that you maybe are unaware that you've kind of been around in organic acid before, vinegar is an organic acid. Vinegar is acetic acid. That's the common name for, or that's the more technical name for vinegar is acetic acid, and it is an example of an organic acid. Now, esters. So here's what we've done. We've done phenols. We have done esters and ethers and epoxides, aldehydes and ketones, carboxylic acids, and now we're moving on to a fifth functional group, esters. Esters are molecules that are formed by replacing the hydrogen of a carboxylic acid with the alkyl group of an alcohol or phenol. Okay, whenever you see this word alkyl, what I want you to think about is, I want you to think about alkanes, alkenes, alkynes. What do we know about alkyls, alkanes, and alkynes. They're nothing but carbons and hydrogens. Okay. So in order to make an ester, you take a carboxylic acid, like this guy right here, and you react it with an alcohol. So if you were to take methanol, that would be CH3OH. I'm going to scribble this out. And then what we're going to do is we're basically going to take this OH on our carboxylic acid and this hydrogen on our alcohol. And these two things are going to come together to make water. Then this acid that I just reacted with, I'm going to form an ester. And so what I have is I have this. Actually, let me go ahead and I'm going to use the highlighter for this. That part of my molecule ends up right here. So to rewrite that, actually, I think what I'll do is I'll go to highlighter, switch the color to white. Where's my highlighter? Oh, no, that's not what I want. Just a second. Okay, so here what I'm going to do now, switch to the color red, CH3, we've got the oxygen there, and CH3. Done. That is an ester. So an ester is basically an ether, but rather than an organic group being shared with, or sorry, an oxygen connecting two organic groups, instead it's a carbonyl, then an oxygen connecting these two groups. So when you think about an ester, I always think about it as these components, COO, but then one organic group is bound to a carbon, and then the other organic group is bound to our oxygen, our singly bonded oxygen. So that is an ester. Now, some examples of esters, these are very common whenever it comes to fragrances. So esters that produce different odors, or examples of esters that produce different odors, are methyl butyrate, ethyl butyrate, propyl acetate, pentyl acetate. All of these substances make, or they have different odors. Banana, pear, pineapple, apple. And you might be thinking, well, doesn't an apple have an odor from lots of different molecules? And yes, it does. There's lots of different compounds that apples produce to give it an overall odor. But these are compounds that can be synthesized. So the way that I think about it is, let's say that you went to the grocery store or gas station and you bought like a apple flavored candy. Well, that apple flavored candy is going to have methyl butyrate. If you bought a banana flavored candy, it's going to have pentyl acetate. This is something that people who take an organic chemistry lab, they typically make pentyl acetate. And I do not like the odor of that. But pentyl acetate has a banana odor or a banana flavor to it. So that's where these different compounds are coming from. So with this information, I don't want you to commit these different compounds to memory. I instead want you to think about this as, okay, we talked about esters, carboxylic acids, aldehydes and ketones, ethers and epoxides, and phenols. Of all of these different functional groups, which one of them is associated with a compound that has a particular odor? Well, that'd be your esters. So anytime you smell something, I want you to be thinking like, oh, that must be an ester. What is that ester? I don't know exactly, but it is an ester. Depends on the odor. But that substance, whatever that material or substance is that's producing an odor, that odor is coming from an ester, or more than likely coming from an ester. All right. So my next functional group that I want you to be familiar with are amines. Amines are derivatives of ammonia. Ammonia, if you've seen that word before, you might be thinking, oh, cleaning supplies. And you're absolutely right. Ammonia is a cleaning material. Now, ammonia has a formula of NH3. Now, that probably stands out to you because, when you think about carbon, carbon likes to form 4 bonds. Carbon might look like this. Methane, for instance, has 4 hydrogens coming off of it. There's a methane molecule. Ammonia only has 3 bonds coming off of it. What gives? Why? Why does ammonia only have 3 bonds coming off of it? Well, the answer to that is that nitrogen likes to hold on to a lone pair of electrons. So nitrogen likes to have 3 bonds and 1 lone pair of electrons. Now, that is ammonia. These 3 bonds are hydrogen when we're talking about ammonia. Now, if you think back to our carboxylic acids, what did we do when we had a carboxylic acid right here with an OH? Well, when we had that H, we replaced it. We replaced that OH, we replaced that H from that OH with an organic group. And that is the foundation on amines. So an amine is coming from when one or more hydrogens of ammonia are replaced by an alkyl group. An amine is the result. So this would be a primary amine, a secondary amine, and then a tertiary amine. So what has been replaced? 1 hydrogen, 2 hydrogens, or 3 hydrogens have been replaced in these different amines. Now, these R groups can be the same, they can be different. One of the things that you very commonly see whenever R groups are different or these organic groups are different is you'll see something like this, R prime. And then you'll sometimes see R double prime. So those alkyl groups are going to be different. Now, like ammonia, amines tend to be very basic. So that means they like to take on protons as opposed to giving them off. And in addition to that, if you've ever cleaned with ammonia, well, then you know that it has a particular odor. And so amines tend to have similar odors, and they tend to have odors. Now, some examples of an amine, these are things that you maybe have become familiar with just based on me saying amine. You might think back to, oh, I've heard that term before, that INE suffix. INE. Typically, when you hear about a molecule with INE in it, that means it's an amine. So what that means is amphetamine is an example of an amine because we've got an H2. 1,6-hexane diamine. Okay, so this is a great question because it's consolidating lots of different things. This is an alkane. More specifically, it's a hexane because does this molecule have any double bonds between it? Let's, before we get ahead of ourselves, let's go ahead and try to draw it out. 3, 4, 5, 6. Okay, so there's my 6 carbons. And then H, 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 and H. Okay, so there's 6 of our hydrogens. So now I'm down to, well, I'm gonna scribble out things that I've already written down. So I've written one of the hydrogens on each of these carbons. I've written all my carbons. One, that, there we go. Okay, so now my last hydrogen, H, 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 H. Okay, so now got all my hydrogens. So here's my chain. This is hexane, nothing but single carbon-carbon bonds. No, it's not hexene or anything like that. And then I've got NH2, N, H, H, done, N, H, H. So this shows us 1,6-hexane. So we've got hexane. I did that previously. 1,6-diamine, meaning two amines. Now, I think a question that we've gone over previously is, well, am I starting from the left or am I starting from the right? My numbering here, 6 carbons. It doesn't matter if I start from the left or the right. Either way, these amines are at position 1 and 6. So this is an example of a diamine, or simply put, an amine. Now, pyridoxamine and cadaverine. Well, cadaverine, if you look at that, we've got 1, 2, 3, 4, 5. Okay. Think for a minute and compare and look at 1,6-hexane diamine. What do you think you would also, or what do you think you could also call cadaverine? Based on 1,6-hexane diamine. Well, my question is, how does 1,5-pentadiamine sound? Now, you probably saw cadaverine and thought, oof, it's a little bit of a unique name. That doesn't follow any of the organic rules that we've talked about. That's not a meth f pro or meth f pro but pent hex. It's not. That's a common name. So that's a name that lots of molecules will basically be granted or adopt in time, just based on kind of their use in like everyday experiences. What does cadaverine do? Well, cadaverine is commonly found in decaying or putrefying fish. So when you hear the term cadaverine and you hear, and I mean, I personally think of cadaver, like what medical students dissect. That's really not too far off because this is a compound that is a breakdown product of one of the building blocks of life, an amino acid. So parts of proteins are broken down into amino acids, and amino acids, or one amino acid, can be broken down into a compound like cadaverine. So that's where that name comes from. I'm sure that it was isolated and then somebody was like, this is the stuff that stinks. Oh, it's awful. Let's call this cadaverine. Well, that brings up a little bit of the context. Well, it's from a cadaver, a fish, and it has an amine. More importantly, this is an example of a diamine. So this is also known as 1,5-pentadiene, which is very similar to 1,6-hexadiamine. Now, I think using those names, that's fantastic because can you imagine what 1,4-tetradiamine looks like? Then can you imagine what, let's say, 1,5-hexadiamine would look like? Now that one's a little bit tricky, and I'm going to erase 1,5-pentadiamine, that name, and I'm going to draw for you 1,5-hexadiamine. Okay, so what we know is it's got two amines. So I'm going to write H2 N, and then hexadiamine, CH2, CH2. Okay, so I've got 6 carbons that I need to draw. And actually, you know what? I'm rather than CH2, I'm gonna do 3, 4, 5, 6. Okay. Now, I think it's safe to say that this NH2 is on carbon number 1. There's no NH2 on carbon number 2. Carbon number 3, nope. Carbon number 4, nope. And then carbon number 5. So 1,5-hexadiamine. Well, on carbon number 5, I'm going to write NH2. H. Then this is where you kind of get into a habit, or you get into a pattern almost, and you think, okay, so this is carbon number 1. This is carbon number 6. Okay, that's going to be H, H. But remember, carbon loves to have 4 bonds to it. So this has a 4th H to it. So this is an example of 1,5-hexadiamine. Now just imagine 1,4-hexadiamine, 1,3-hexadiamine, 1,2-hexadiamine, and then maybe even 1,1-hexadiamine. What would that look like? Well, the good thing is we can say 1,1, and I can take that hydrogen, that NH2, and put H, and then NH2. There we go. There's 1,1-hexadiamine. I've got 6 carbons. I've got 2 amines on carbon number 1, which is indicated by 1,1-hexadiamine. I can take this one more direction. Let's go ahead and go with 1,1,1-hexatriamine. Let's erase that. That's just a 1. I'm erasing that 1. NH2. So there we go. That's 1,1,1-hexatriamine. Now, does that tell me where all my amines are? It does. Does it tell me how many carbons I've got? It does. Now, as you can imagine, if you had a molecule that had like 9 amines, does the name get more complicated? Does it get to be a long name? It does. Because then you're talking about, well, I've got 9 amines. You got to think about your prefix. Octo, non. 9 is non. So then it'd be nonamine. If you had, and then you have to put the numbers where they're all located. Now, amides seem like these are very similar to amines, but what they are is they are very similar to a combination of a carboxylic acid and an amine. So an amide has nitrogen bonded to a carbonyl carbon. Okay, so here's I always like to build these molecules up. So we have a carbonyl carbon. And then we have a nitrogen bonded to it. Okay, so that's basically our foundation for an amide. Now, the amino acids of proteins are linked by amide linkages. This is something, this bond right here is super common in any and every living organism. If you drink whey protein, or if you drink a shake with whey protein in it, congratulations, you've consumed something that has an amide group, where we have a carbonyl carbon and a nitrogen. Now, with that in mind, that's going to make this amide. So that amide is going to be, here is a functional group, or here is a organic group, and then we've got H and H. Now, the cool thing about this is this right here. This is a simple amide because we've got that amide linkage. But when we jog back for a second, when we look at our amines, well, the different groups on your amines can be highly variable, and they can be, well, very different from one another. I got to change that. They can be very simple, or they can be much more complicated. Here, what we have is the spectrum or the range of amides and how simple they can be and how complicated they can be. A simplified amide has our carbonyl carbon and then NH2. A slightly more complicated one has, in place of one of those hydrogens, what does that R prime mean? That R prime means an organic group. That could be an alkyl group. That, let's just make it simple and let's say that this is CH3. So CH3, boom, that is different. Okay. Then we could also have two different groups coming off of that nitrogen that's a part of our amide linkage. So this is just illustrating how complex, but also kind of how simple these things are. Now, what we have covered today, let's go back to the very beginning. What we covered today, and actually, let's see, 9, 5, and then 9, that would be the 10th. Today, ethers, aldehydes, ketones, carboxylic acids, esters, amines, amides. So if you remember on our last PowerPoint, I showed you a list of the supporting cast functional groups and then the main characters. Those, don't worry about that list. Instead, focus on this list that's here. Now, I'm happy, like, these are showing all of the different functional groups. There will be lots of questions on your exam that are simply identifying a functional group. And an example of that would be something like, let's go with, I'm going to draw a molecule real quick. 3C double bonded O, and then O dash CH2, then CH2OH. Okay, so an example question that you should expect to have on this first exam would look something like this, where I give you a molecule and then put a box around this, and I'll label that as A. And then I'll put a box around this, and I'll label this as B. And then I'll put a box around, let's see, I'm going to get one more color just to give contrast. Give that whole thing. And then that would be labeled C, just as an example. And then, let's see, I'll go with one, well, I'll stop right there. And then a question that you should anticipate having would be something like, what functional group is, or what group is captured in box A? In which case, is that one of the things that's listed here? No. But is that carbon double bonded to an oxygen something that we've learned about? And is it central to aldehydes, ketones, carboxylic acids, amides, and esters? Yes, it is. A is a carbonyl group. Now, that's the sort of question that I want you to be able to answer. So if you feel good about all of these functional groups, that's going to be extremely helpful, but you're going to be applying them. You're going to be using those groups and identifying them somewhere. Okay. On Friday at, I believe it's at 1 p.m., we're going to have a review session. I'm going to work through a review document, and then I'm also going to field any questions that you have. I think what I'll do first is I'll field questions, and then I'll just start working through the review document. And then your exam is going to be on the 17th. So if you have questions on the 16th, let me know. We can meet on Zoom. We can talk about it. But that's what's kind of on the horizon in the next couple of days. So with that in mind, I'm going to go ahead and stop my recording. And if you have any questions that come up over the next few days, please contact me so I can help you out, so I can, maybe provide some more clarity and examples. All right, well, I hope you have a good one.